mean by that? What we mean by that is the specification of a dream. Like I want to have some sort of data type, and I'm talking about this data type in an abstract way. I want, for example, this data type to hold big integers and be able to add them and subtract them. And I'm completely not interested at this point how somebody is going to implement that. So today we're going to learn to study two different abstract data types, and we will see that we can implement them in several ways. And the implementation, of course, is going to influence the complexity of operations on this data structure. So today we're going to talk about abstract data type called Q. So as we said, the process of abstraction is the model sub-real life entity in an abstract way, in such a way that only contains the most important features of this entity. So imagine that somebody wanted you to create this, this kind of automated queue in the doctor's office when they take numbers, and everyone who comes last receives the last number, and then they get called from the beginning of the queue, from the front of the queue. So if these are the only requirements, nobody asked you to be able to access a patient in the middle of the queue, the third patient or the fourth patient, right? You only need to have two ends in this data structure, right? At one end we add, at another end we retrieve. There are two opposite ends. If these are the only two required operations, then we can model in our head the doctor queue using abstract data type called queue. The elements in the queue are sorted by the timestamp of their arrival, from the earlier to the later. The order of adding elements is the same as the order of their removal. See, like I'm adding at the rear and I'm removing from the front. If A was added first, it's going to be removed first. B added second, going to be removed second, and so on. This idea is called first in, first out queue. FIFO queue, FIFO queue. Good. So let's write the specification, abstract data type. Q, abstract data type which supports the following operations. NQ adds element E to the collection. DQ removes and returns least recently added, the oldest element. Then there are two read, one read operation called either pick or front. In different sources, it's called differently. It's just like, can I pick at the first element in the queue? I'm just checking, are you still there? That's all. Is empty? Are there any elements in the queue? Is full? Is any space left to add elements? Look at this specification. Nowhere does it say, how do I need to implement queue? What actual arrangement in memory I should implement. This is an abstract concept. I want to be able to do all these operations, and I call this abstract concept queue. Okay, so now after we receive this specification, we are going to try to implement this specification using different data structures, and we know only two of them, array or linked list. So let's see how we can implement Q using an array. So an array. For QADT, we need efficient access to two opposite sides of the sequence. Now try to kind of remember, what did we say about an array? Is there one side of the array where adding elements is easy? Can you try to remember? The cheap, where like in the beginning of the array or at the end of the array, where it's cheap to add a new element?
End of the array.
At the end of the array, right? Like as long as there is space, we just place it in this position size in the array. So in the beginning, adding is really, really expensive because then we need to shift everything else. So now, how about removing element from an array? Which side is easier to do? Less time. At the end of the array or in the beginning of the array? Array is, look, nobody knows, or you just don't want to talk?
Is it the end again?
At the end. Okay, so see, the array is not a very nice data structure. You just see this at the end, I can add and remove easily. In the beginning, I can't add or remove easily because it requires me shifting elements. So array is not a very appropriate data structure, it seems, to implement queue because I need two different ends. See, no matter which end I choose, one of them is going to be the end at which I add, and another is going to be an end from which I remove. So how do we get around this problem? So we're doing like this. We can add remove elements efficiently at the end of the array. Let's say we choose a queue at the end of the array and the queue from the front of an array. While adding element to the end of the array is generally cheap, removing element from the beginning of the array is very expensive. It's big O of n. So just one removal, you remove one patient, and then you would need to shift n patient to the front of the queue. Okay, so there is a problem with the queue. So what do we do? There is a solution which is called circular array. So we are going to have two pointers. These pointers are just indexes in the array. Indexes in the array. Originally, the read pointer points to position 0 and the write pointer points to the position 0. Those pointers represent where are we going to read the first element of the queue, and where are we going to add the next element to the queue? Where in the array? So originally they are all 0. So now, if I want to enqueue A, I'm going to place it into position indicated by right. So see, I'm indicating it by right, and I increment right. So now right is pointing to the next slot in the array. So in this way, see, I have two pointers in the array. One represents the place from which I read, and another place at which I add. So here in QB, the right will become B. So see here, the Q, see, in order to prevent shifting, I'm going now to remove A from its position, and I'm going to move read in one operation. The read is now going to be pointing to 1. See? That's going in circles. So there are like just two pointers, and some in between them there is a queue. In between 1 and 2 is a queue. However, I never shift the elements inside the array. I just represent the ends of the array in this circular manner. So I removed the A, and now my read pointer is at position 1. Okay. And how can we implement another idea? So we learned how can we implement abstract idea of a queue into different ways, and now we are going to see how we can implement another idea. So what is this idea? What are we modeling here? Let's say there is a situation when you are asked to create a program to keep track of the employees roster, human resources roster. And let's say that in this particular roster, nobody cares about employees at all, and only thing we care about is adding and removing them. So when the company grows, we add a new employee to the end of the stack, right? Like this. And now to the end of the roster. And then when the company downsizes, we should be able to remove the last added employee. Because in this company and everywhere else in the world, there is a seniority principle. The last added person is removed first, is fired first. The recently hired person is fired first. So that's the person disappears. So then if these are the only requirements for your HR roster, we can implement this idea by using an abstract data type called stack. So if these are the only requirements, then we can model it using stack ADT, stack ADT. Stack stores a sequence of elements and allows only two operations. It does not allow you accessing elements in the middle of the sequence. It only allows you two operations, adding a new element on the top and removing the element from the same top. The elements are removed in the order opposite to this arrival, from recent to older. This is an example of something which is called LIFO-Q, last in, first out. The other Q was called FIFO-Q, first in, first out. Whoever was added first is going to be removed first. Here, whoever was added last is going to be removed first. So this is one-ended kind of data type. Take only one end interests us. We are interested only in one end. So stack, here is specification, an abstract data type which stores some collection of elements and supports the following operations: push and pop. Push adds element to the collection. Pop removes and returns most recently added element. It also has these read operations, which is also can be called pick or top. See, here it's called top. In the queue, it was called front. Here is called top. Look at, we can kind of imagine stack as a vertical stack of plates. Like if you stack the plates on your table, you will not be able to remove the plate from the middle, right? You only can remove it from the top. And you can add a new plate on the top of the stack. It also supports is empty and is full as before. So, okay, so how do we implement stack abstract data type? Stack is a special type of a sequence where elements are sorted by the timestamp. We do not have access to the elements in the middle of the sequence. We need an efficient access to only one end of the sequence. This idea can be implemented using either an array or a linked list. So let's see, an array. Implementation with an array. So then we only need one end, so we are going to use the end of the array, because that is where the efficient operations happen. Push A is added, size is 1. B is added, size is 2, so we always add at position size, you see? So pick, if I want just to look at the recently added, that is going to be at position size at the end of the array. Well, what was the, on top of this stack? What is there? Is B. Push C, we can push C, right? And then we pop. When we pop, we just remove C. The addition and removal both happening at the end of the array, which is extremely cheap unless we resize the array. Push D, push E, and push. So that's kind of not difficult, right? And now I want G, and it's full. It's either is full is true or we resize and copy that to a new, more spacious array. Okay, so here, yeah, that we need just to resize the array. So it's the answer to this question. So, okay, so now pop, you see pop is going from the same end, completely cheap and nice, and pop, 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 and when size is 0, is empty, returns true. The size is 0. So this is a implementation which doesn't require much work. We just use an array, one end of the array, to push and pop. So all the operations, if no resize is required, run in time big O of 1. Constant time operations, very efficient implementation of a stack using an array. So how about linked lists? Okay, so here is an idea. So I can add at the end of the list, but then I am going to be needed to also remove from the end of the list, because it's one-ended queue, one-ended. Okay, so then I push A, so I'm going to add actually things on top of each other, see? I'm going to add to the head all the time, see? Because now I need to remove list recently added, like this is my sequence, right? My sequence was like A, oh, that doesn't work in this. Sequence that I store here is A and then B. So B is last recently added. So when I'm going to pop, I need to remove B. That's why I'm going to always keep the last element on top of the linked list, on top, because this is the head of the linked list is the only good place to remove elements. The elements can be removed in a constant time only from the head of the linked list. So when I push C here, I'm going to add it here. See? Even though the sequence itself is ABC, but they are stored in this order. Because whatever I add last, I need to be able to remove first. Last in, first out. And again, of course, this happening only because it is more efficient. Like in principle, I could have added at the tail, but then I would need also remove from the tail, but it's not very possible to do it efficiently. So pop, see, then I remove in one operation. So that is kind of good implementation of stack ADT. The cost of operation is big O of 1. So we have two alternative implementations for both stack ADT and queue abstract data types. Any questions about that? Summary. Abstract type stack can be implemented either using an array or linked list. Each stack operation is big O of 1, push, pop, pick is empty. Considerations. Linked lists have storage overhead. However, arrays do have a limited storage, which they need to be resized when they are full. So it's your choice what you choose here. Here, both of them are easy to implement, basically, all of them. So now we're